that here. You can see his signature outside. It's very funny. And he works in Melbourne University and in the psychological science. And he is very good at categorization. I'm using the LBA model to do some categorization tasks. And also SFT, systems factorial technology. We just introduced this technology last year. So now just welcome Daniel.
Thanks, King Todd. Happy birthday. Thank you for inviting me here. So I've uploaded to the server for the NCKU Math Psych workshop a zip file that contains some files that we can use for some of the demos, which I'm going to talk about later. So what I'd like you to do is go to this URL. If you click on it, well, you have to type it into your browser. If I click on it, then it should open up for me a link. There it is. It'll go to the Google Drive where the files are stored, and you can download this zip file called little demo NCKU maths.zip. And download that onto the machine you're using and make sure you know where it is. What we're going to do then is go into your instance in the browser of RStudio on Andrew's server. Click upload. So this is in your browser, the one that you've been using for the entire workshop. Click upload. Did you see where I did that? Upload is right here. If you have your list of files, then you can click upload. Select the zip file. Under choose file, you should select the zip file and click OK. And that will take 30 seconds or so to upload the zip file. And once you've done that successfully, you should have two folders now alongside the DMC folders called RGRT demo and RMDS demo. Has anyone done that successfully? Great. So if you click files, now you can click upload. Yeah. So if you're looking at your plots that you created when you were doing stuff with Andrew, you might have to click back to files first to get to the upload. Yeah. So you're looking at the wrong thing here. So if you go back to files and then click upload, you can upload the zip file. Yes. Oh, yeah. Or you upload it into the directory. So those are two folders inside the zip file. So if you just click download at the top, that'll download. Well, you've already got it. You go on. Yes. So now go back to your RStudio. Click upload. And just choose one of those. Not that's an HTML document. So where is that? That's just file. Yeah. No problem. Can we go to where you have the click that word? Yeah, no, not here. Yes. Go find that file and you click upload. So you have to go to that folder.
How is that? How is that?
I make no.
Go back over, we can do this off-grid so you
You can't upload that onto RStudio.
can send me some questions.
Does we select RStudio multiple choose? That's not zip file. You can, if you can't get it to work, what I'll recommend is that you just follow along with me and we can fix problems like using Macs instead of Windows.
You didn't do it the server?
Yeah. So I've got it loaded up here. It's on the server. Some people we've got it loaded working on Windows, but when you download the zip file on Mac, it automatically unzips it. You don't have the file. So I'm not sure how to handle that.
Right click and press. Right click on the folder and press.
Yeah. So if it unzips and you right click on the folder and press those two folders and upload that.
Load it up. In fact, our studio, we just tell our studio to upload more than 2 files of the folder, it automatically zips itself.
Yeah. Well, for this one, if you click upload, it says upload a zip and it'll unzip the folder. So yeah, if you want to do multiple files, you can do it. Oh, good. And did you get it with completion? Great. Okay. Yeah, there's okay. So if everyone's at least got the zip file downloaded, then I'll leave you to try to fight with your browser to get it set up in our studio while I kind of introduce the topic I'm going to talk about. So I'm going to talk about a specific application of the types of response time models that Andrew introduced. And I'm going to talk about a slightly different way in which to use those models. And I'm going to link the use of those models with some other techniques, some other well-known statistical techniques, and some other kind of psychological process modeling techniques, where our goal is not only to try to explain where the RTs came from, or the process that generated the response times, but also to explain the process that went into generating the drift rates, which control that process of generating the response times. So I'm going to spend the first part of the talk just sort of introducing this idea of mental representation and how we can do operations on mental representations, how we process information based on these representations, which leads us into the decision time process, the response time process, and the decision-making process. Now, I'm going to set up this dichotomy between these two things. Really, they operate together. Andrew will have talked about the RT component of the information processing and decision-making process, but I'm going to talk about the mental representation process. And then, if we have more time, if we can get through the first set of demos, I'll talk about some more complicated things. Hopefully, I'll show you a bit of Bayesian analysis, Bayesian hierarchical modeling as well, given that that's what the name of the workshop is. Okay, so I'm going to distinguish, this might be the hardest part to understand about the whole thing. So I'm going to distinguish the sequence of things which happen when you make a decision into two parts. One of those I'm going to call the processing backend. So this is the bit which actually takes the information from something, processes it, and generates your choice and the amount of time it takes to generate your response time. Now, I'm going to call this the backend, and I'll show you why I'm going to call it the backend in a minute. So this processing backend is going to encompass all the bits, all the different mechanisms which underlie choice and response time. It's going to take into account things like the information processing architecture. So how do you combine the information? What are your decisional biases in making those decisions? And really, these types of backends are all going to be things like evidence accumulation models. Things like the drift diffusion model, the DDM model that Andrew talked about, the LBA, the log normal race model that Andrew introduced as well. And I'm going to distinguish that from something which I'm going to call the representation front end. So this is the representational front end is really going to capture how do we take information from the environment and represent it mentally in a way which captures the types of similarity relations between different inputs in the environment. And then how does that representation then feed into the back-end processing component? So the way Andrew described what was happening with response time models is that you got a drift rate, which represents the information that you're getting from the stimuli. If you have to make a decision about cats and dogs, and your drift rate tells you how much evidence do I have that this is a cat or a dog. What we're going to try to capture is how do you actually represent cats and dogs in a way which allows you to then pull out a drift rate, which then feeds into an LBA model or a diffusion model or so. So does that concept of front end and back end make sense? Can you translate that idea? Wait, let me show you something else that might explain this better. So this is the response time component of the model. You've seen this before in Andrew's part of the workshop. So this is what I've drawn there is a drift diffusion model, and the parameter that you get out here in the part that Andrew showed you was just a parameter that you set a distribution over, and you did posterior inference on that particular parameter. But we can build an entire model that's used to tell you where does that drift rate come from. And this particular model is a model which attempts to integrate some aspects of early sensory processing, so early visual processing, and this early visual processing then drives how much evidence you have for one choice or another. So this is a model by Philip Smith and Roger Ratcliffe. And the way this particular model works is a stimulus is presented for some amount of time, and there's a function which controls the sensory response. So you can think about this as sort of a retinal response, V1 response, so activity building up in those areas. In this particular task, they were interested in visual masking, so at some point in time, a mask would come on and cut off the amount, that sensory response function. And that information is then passed to visual short-term memory. So you can think about this happening all at once. So as this stimulus comes on, your visual short-term memory representation starts to build up over time, which means that the evidence that you have for each of these choices is building up over time as well. And they're attempting to capture here how does the attention system and the visual short-term memory system essentially compute a drift rate in time that drives the decision process. So the decision process here is the back-end model. And all of this other stuff that has to do with visual attention and visual short-term memory is the front-end model. And the reason I'm talking about it in that way is because we can take out this bit and put in something else. So we can take out the DDM and put in the LBA. Or take out the LBA and put in the log normal race. And keep all of these other processes the same. So that's sort of might not work as well for this model because all of this information is flowing in continuous time. This particular model is quite complex. But the other models I'm going to talk about have this kind of hot swappable component. So it's like a computer and a printer. You get a new printer, you plug in the new printer, and that spits out the pages. You can change the front end. You can maybe plug in a different computer in the front end, so that would be the front end component, and but keep the same printer at the back end. And these things are hot swappable in the way that I'm going to talk about. Okay, go.
好，所以其实我们在解释那个在讯息处理到最后决策的过程的时候，可以把它分成一个是前端的，一个是后端的处理。那 Andrew 昨天讲的这些东西，其实是比较后端的这些东西，就是讲我们的讯息已经进来之后，然后你在做决策的过程之后，这些讯息是怎么累积的。所以不管是 LBM model 或者是 DDM model 或者是 LNR model， 都是在讲这个讯息累积的过程。那昨天有提到一些参数，在描述这个讯息的累积过程，像是阈值，或者是起始值，或者是累积的速度，这个都是在后面这些部分的。那其实还有很多前面的处理，像是知觉的处理、注意力，或者是工作记忆等等的这些东西，其实我们有很多心理学家已经做出了不同的 model 在解释这些东西。那我们就是看说，我们有这个非常前面这些东西，要怎么跟这个后端的东西连在一起。那你后端的东西，你不管你是靠 LBA 或是 BBM 或者是 LMR model 都可以。那我们现在就是要怎么把 front end 的东西跟 back end 的东西结合在一起。
So why is this important? Why do we want to understand the similarity relationships between our inputs? Well, here's a really important example, which is contrasting the physical representation of light with the psychological representation of light, and in particular colors, so wavelengths that form the color spectrum. So you can produce all of these colors simply by varying the wavelength of light that you're presenting. But people do not represent the similarity between colors on a unidimensional continuum like this, because we actually see the color purple and the color red quite similar to one another. We actually see them as similar. So if you think about how people represent the similarity between colors, it actually forms Newton's color circle. This is true even if you kind of transform this through early visual opponent cone processes, looking at short and medium and long wavelength opponent processes. And even that is not an accurate representation of how we consider similarity between different colors. So if we think about if someone has to categorize a set of colors based on their properties of, let's say, redness or greenness, then you might think by looking at this particular diagram that you could just put a boundary between red and green, and that anything up on this end would be considered more green than red. That's not true. That's not how people would actually do this task. Instead, they might put a boundary through this space, in which now purple and red would be more likely to be considered to be similar to each other and members of the same category. So what we want to try to do is capture this similarity relationship in a way which allows us to explain how people actually do form categories and how the response times from a task like making category decisions actually happens. So there is a model which does this. It's called the exemplar-based random walk model. Now the background model is not the drift diffusion model, but it's a discrete approximation to that called a random walk. It's a sort of like the dumb cousin of the drift diffusion model. And the front end component of it is called an exemplar model. And in an exemplar model, the way in which the model works is it assumes that you store items in memory. Whenever you have a new color to categorize, you compare it based on its distance to everything in memory. You convert that to similarity. Then you take the ratio of the similarity to the category A's to the A's and the B's, and that determines your drift rate. So it's not important for you to know the details of all of this. I just want to get across the idea that there are models which consider this similarity-based component. In newer versions of the exemplar-based model, they actually take out the random walk model and put in something like the LBA instead. So how can we understand what that representation actually is? And I'm going to talk about two different methods for doing that. These are the first is called multidimensional scaling, and this is a statistical method that's used for taking a set of data describing the proximity between sets of items and then visualizing what the distances are between those items. And I'll show you a few different approaches to this. An alternative to this is general recognition theory. And the bit that I really want to get to and introduce is at the end, which combines aspects of multidimensional scaling and general recognition theory with a process model of response times. And what this is going to do is allow us to use response time data to determine what people actually see as the similarity relationships between the inputs. So we might get there. At least I can tell you about it if we don't get to take a good look at it. What I want to do first, though, is just tell you about classic multidimensional scaling. Has anybody used multidimensional scaling techniques before? Great. Great.
多项度量化方法，这是在那个多变量分析的时候会教到的一种方法。所以它其实就是算两的相似性，然后把东西表征在一个空间上面。那简单的来说，你可以看就是说那个简单的例子。
高雄的台南跟台北做的概念，但是这个是心理的感受，只是它跟你的物理距离事实上是有一种对应性的关系一样的。你在那个心理的地图上，你看起来是从这两个点很像，那位置越接近就越像，位置越分离的就越不像。
所以它就是把那个相似性换成一个可以表征在空间上的一个距离的概念。所以刚刚那个你们在看颜色也是一样嘛，它颜色在物理量上面是一个单向度的随着波长变化的一个物理刺激，但是在我们心理空间表征的时候，它可能就是一个环状的东西。那所以我们的心理表征，它把物理刺激用一个方法把它变成我们心理的。
有的时候那个心理的表征的空间的坐标，它的长相不一定跟你的那个物理的坐标长相是对应的，可能刚好偏斜了，或者甚至是有本来是四方形的变成膨胀成圆形的都有可能。但是它是主要是想办法让心理感受在用物理的这个不是法，让它能够实际的这个具体化出来，让比较容易可以分析它。
Okay. So our goal is to go from something like this and uncover what people do psychologically, how they represent us. The method that we're going to use to do that is to first take some proximity data. And what do I mean by proximity data? These are just, they can be lots of different things. So we might, for instance, take a set of colors, so red, green, blue, yellow, orange, and so on. Show them to people in pairs and ask them, how similar do you think these things are? And they will rate from 1 to 7. 7 will be very similar, 1 will be not similar at all. And we will do this for all of the pairs. And we'll get a matrix of numbers representing, for each pair, what was their similarity rate. And then what we want to do is use that data to find some visual representation of a set of items. So if we have 7 colors, then there are 7, choose 2 different pairs. So that ends up being 21 different pairs. And we don't want to represent similarity as 21 different things. We really want to have a nice, potentially even 2-dimensional or 1-dimensional representation of what those relationships are. So that we want to reduce the number of dimensions that we're actually thinking about. To capture a lot of the variance in those similarity relations, but without necessarily taking into account all of it. Okay, so I'm going to give you something which to think about. Here we have 2 different dimensions. Each one of these stimuli vary on their saturation. So these are very unsaturated, these are very saturated. Is the concept of saturation? And orientation. And in all of the examples that I'm going to talk about, I'm going to number these like this. So they're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 across the bottom, or from bottom to top. So what we want to do is look at some similarity comparison data. So I have some data that are in the zip file where we took these 2 at a time and asked people, how similar do you think they are? And what I want to show you is a few different methods for getting at a figure which shows you those similarity relationships. Now you might have noticed that the steps between these pairs and these pairs are not the same. So these pairs are closer together than these. So there's a step of 4 between this set and a step of 2 here. Same thing with the orientation. There's a difference of 20 here, but only a difference of 10 here. So what we want to know is, whenever we do our analysis, does it actually are people picking up on this difference in spacing between the same? Okay, so the first method we're going to try, just to introduce the problem, is the classical multidimensional scaling method. This is really the first one, which was invented by Torgerson in 1952. It's a lot like principal components analysis. If you want to know I haven't put the math in here, but I put the steps that go into the math. What you have is a number of objects with a certain number of dimensions. You find the distances between each of those objects. You do a double centering of the distance matrix, don't worry about that. Then you do an eigenvalue decomposition. This is just like principal components analysis. You keep the eigenvalues and you keep the eigenvectors with eigenvalues greater than 0, and then you recreate the coordinates using the reduced matrix. It's very easy. It's built into all statistical packages. R already has a program built in to do this. It's an analytic solution, so it's very fast. What it actually does is minimize, well, you can think about what it's doing as minimizing an error function. So Andrew talked about Bayesian methods, and he talked about maximum likelihood methods, where we're doing this hill climbing algorithm to find the maximum likelihood. You can think about what this is doing is minimizing an error function. So it's climbing down the hill to try to get the error as low as possible. This is an older method. The newer maximum likelihood methods really kind of replace this style of thinking about optimization. And the Bayesian methods are now in replacing that method. So let's actually work through this in R to see kind of how things are set up and just to see how this works. So if you go into the MDS demo and go into the function called MDS-demos.r, this will have now a bunch of commands in it. Now, I'm going to assume that some of these packages are not installed on the server, so we're going to need to modify this code a little bit in order to do that. Okay. It worked earlier. So, what I want you to do is remove the hash symbol from in front of lines 5 and 6. So whenever you run this, what it will do is install these two packages and then load them into a library down here. Now, one of the things that we may, this should work, I'm hoping this works, is getting the directory correct could be, you don't have, I know you don't have the library, you need to install it. You need to remove the hash. There is no library called crackpot. So let's just try running this first bit. Only run lines 5 to 6. Okay, so this is going to ask if you want to restart R prior to installing. You can click no here. Click no twice. And let's try that now. So that will take some time to install, and you'll get a bunch of red messages in the console. Now let's see if we can load these two libraries. Then they should load fine. So let's see if I can do that on my screen. So this will, you might get this pop up. Click no. You'll have to do this twice because we're installing.
好了以后你就放第8、第9。
No. So that's
有没有人有问题的举手一下？
they don't have it.
对，你刚刚都是照到我
No,
的手，
they do.
然后再来乱发全部所有人也都是。
Everybody load the libraries okay? Once you get going? Okay, and the next little trick that may or may not work is getting this to redirect to the right directory. Now I've set this up so that you've been running Andrew's VMC and your temp WD should be set to the main install directory so that we should be able to go into the R file. You can't change the directory.
I know because I was in the wrong directory.
So you have to go to
Because I
-5
was
and 6
in the directory before I upload.
and remove the hashtag. But you can copy them one at a time. So you just put run them. Yeah, so that will work. That way, but you have to do the other way too. Yes, that's okay. Yes, this is fine. So your WD should take you back to the main directory. So let's go back to the main directory now. Not change it. Oh, okay. So let me see your file. So you've uploaded it here. So let's upload it again. Yeah, the same file. So let me show you one more thing that needs to be set up in order for this to work. Your folders, whenever you upload the file, your folders need to be in the same directory as DMC and tutorial. If they can't be in, you can't already be in the tutorial directory and upload the zip file there. You have to upload it into the main directory. Sorry, I should have mentioned that. So let me see.
You
Now,
have to post redo it and just choose. No, you have to use this that one is run directly.
oh, you are in the correct directory. Yes, so now you can run the rest of the file. Yeah, okay. Again, if it's not working, you can follow along with me. And we'll walk you through all of the parts. Okay, so one thing you might want to check before we continue is you want to check that we're in the right directory. So if you can type get WD brackets like that, then you should see that your current directory is something like home, NCQ account. You'll have your own unique number there, I think, and then R MDS demo. And if you're in there, we are ready. Okay. Okay, so what I'd like you to do now is let's run lines 17 to 22. And I'll explain what's going on. So yours has not uploaded zip file. So that is, it should, oh, I didn't unzip it. This is okay. Yeah. 22, and that will read in our data file, which is some similarity data. I'll show you what that looks like. It's actually this one. I didn't run that. Okay. So you should be able to see those. Just try one. Just do try the MDS. Okay, so this data file has a bunch of columns in it. They're just like a data file you would get from any experiment that you may run. There's a subject identifier, a condition column, a block column, trial number, our two stimuli, so which pairs of stimuli are we showing, and what they were actually rated. So on the first line we've got stimulus 4 compared to stimulus 8, and that was given a similarity of 6. So let's think about what that means. So that means that people rated, when they were shown this stimulus, this subject on this trial, when they were shown this stimulus and this stimulus together and asked how similar are they said on a scale of 1 to 8 that they were a 6. And they also said that 3 and 8 were a 6. So these data are noisy. They're not necessarily going to be able to capture this exact relationship. On trial 2, if you look at it here, you can see that on the second trial they were shown stimulus 3 and 8, and that was also a 6. 9 and 2 was a 5. So there is a lot of variability in what they actually rated. Let's see if we can get a repetition here. I'm not seeing one pop out. So, but these were repeated many times in this particular study. And each time it was repeated, they wouldn't have necessarily given the same answer. So the data are variable. So this would be if we didn't actually, for this data there is only condition and block. I think there are maybe 3 blocks in this data, and there's only 1 condition. So in this study we did run multiple conditions, but these particular set of stimuli were called condition 1.
同学，我跟你们讲一下，所以你们如果有成功load data 之后呢，第一行是它的 subject 编号，第二行是它的 condition， 这边都是1，所以不会用到。然后 block 就是因为它有分3次做，所以有3个 block。然后 S1 跟 S2 就是分别它要 rate 的 stimuli， 所以它要比较 S1 跟 S2 它到底有多像。所以最后的那个 SIM 就是指的是它们1到7分它们像的程度。所以你觉得这2个像不像？然后你就评1到7分，1可能是很像，7可能是很不像，所以你就会得到。
8 is the most similar, 1 is the least.
8分是最像的，然后1分是最不像的，所以就是两的相似性的比较。那有些可能你会看到它不会是每一次都是一样的，所以会有一些变异存在。那我们就是用这些两比较的那个相似性的分数，去用这个资料去用 MDS 的方式去把它的那个 representation 表示出来，用图示的方式。
Okay. So once we've rendered the data, we're going to take this data and we're going to turn it into that matrix that I talked about a moment ago. And that happens on lines 24 to 34. This is going to, if you run this, this will create a matrix called SimMat, which is actually a dissimilarity matrix. If I can show you what SimMat looks like, you'll understand what I mean. Yeah, so it's going to the screen to make that clear.
所以那个 个 C map 就有点像是一个相关矩阵，所以就会有1、1、2、1、3、1、4，然后一直到9个，我们总共有9个刺激嘛，所以就是9乘9的相关矩阵。那对角线会是1，因为1跟1是一样的东西。
So each one of these entries represents a pair of stimuli, and it represents how dissimilar those stimuli are. So the classical multidimensional scaling function in R requires a dissimilarity matrix. So I've just taken 8 minus whatever the average scores actually were for each pair, and I've made it symmetrical. And you can see, for instance, that stimulus 1 compared to stimulus 4 has a dissimilarity of 1.167. So that's pretty similar. So if the maximum dissimilarity now is 8, but if we look at the difference between 1 and 9, they're the most far apart. They have a dissimilarity of 5. So they're the most dissimilar in this particular setting. So that the data makes sense. If we look at the data, that actually makes sense with what we might expect. What we're going to do now is just fit the classical multidimensional scaling model and plot the output. So in R, the classical multidimensional scaling function is called CMD scale. We're going to give it as an input our similarity matrix. We're going to specify that the eigenvalues are true, I think. The nice thing about R is that it's well documented, so if you don't know what something does, you can stick it up. What is I? Also, eigenvalues. Oh yeah, so we're going to get R to return the eigenvalues if we wanted to look at them for some reason. In the default, it's actually turned off, but I'm going to have it return them. And this last number here specifies how many dimensions do we actually want to reduce this to. And I'm just going to specify 2. In this particular study, we told people up front, these squares, these rectangles vary in their orientation and in their color. So people knew going into it there was only 2 things going on. So if you were dealing with something more complicated, like for instance faces, where there could be an infinite number of things going on, you might have to try a number of different dimensions and see how much variance is accounted for by each particular solution. So if you run lines 36 to 46, this will run the classic multidimensional scaling. This will run very fast because there's an analytic solution, and it will plot the outputs in your plot window. Oh, so we got an error. Oh, my margins are too wide. Right, so let me try again. Okay. So this is now plotted my points from my classical multidimensional scaling solution. I've numbered them in the same way that I called them before. You can see that they line up pretty well with where we thought that they should. But they're not quite falling on the grid like we might have expected them to. There's a little bit of compression here, so 6 is sort of focused inward here, which means that it's actually somewhat similar to 5. The scaling solution, is there a command to make the axis square?
Not that I know of. Oh, you can drag around the picture until it's squarish.
Yeah, that'll work.
No, that's the side. Yeah, it's sliding. Yeah, there is.
So this is what, if we squared up our axes, this is what it would actually look like. And you can see that it is sort of picking up that the distance between these is closer together than the distance between here and also here and here, just like we pointed out in our initial study. Oh, oh yeah.